Alright, so we're going to look at using Excel in 3 videos that are coming up in the next series of content. We're going to look at how we could use, say, Excel to evaluate the Laplace equation, that is our gradient squared of the some function being equal to 0. Okay, and those 3 examples are going to be groundwater flow, flow underneath a sluice gate, and flow through an air tunnel. So in our first example, we're going to look at some groundwater flow. So what we're going to do is we're going to assume that we have some rectangular piece of ground that somewhere at some site, and we've gone and done some investigations where we've put up some piezometric devices that measure the piezometric head along the northern, eastern, and southern boundaries. Okay, and we measured a value of, say, 100 on the north side, 50 on the east, and 75 on the west. We don't know what the values were here, but we're going to assume that the flux, so the gradient, so dH by dy in this instance, is 0. So we've got a Neumann boundary at our southern end and Dirichlet boundaries around the site. We can then solve our partial differential equations, and we can develop lines of constant h. In other words, this will tell us how the water is flowing. We'll also then look at what happens when we come back to the site and measure, say, somewhere else, 2 other samples. And once we gather measurements for those, how does that affect the spatial distribution of the groundwater flow? Okay, just though, if you look at this example, how could you use physical reasoning just to get an idea of the direction that the flow is going? Think about it. In the second example, we're going to look at flow underneath a sluice gate. And this time we're going to look at the Laplace equation applied to streamlines. That is now nabla squared or del squared psi equal 0. Okay, so for this instance, we're going to specify the streamline values at the top, how they the values of them in the vertical direction, in the horizontal, and then we're going to look at how we can actually try and model the effect of a sluice gate. In other words, what is the value of the streamline at the sluice gate? And we're going to assume a Neumann boundary at the end, so a no flux boundary. And we're going to explore what happens as the streamlines converge underneath this sluice gate. And you've already done this in some of your fluids lab experiments. So now you can visualize this numerically and visually. Okay, and lastly, we're going to look at a flow through an air tunnel. Okay, so here we're assuming a no-slip boundary condition, that is the velocity at the ground level is 0. We're going to assume as well that there's a linear decrease in velocity, or increase if we were in the vertical direction, to our free stream velocity at the top. And we're going to set that to 200, say, centimeters per second. And we're going to assume as well that our east and west boundaries are far enough away from each other that any disturbance that we apply to the center of our domain is far enough from the boundaries that its effects are negligible. Okay, so as I've already hinted, once we have our linear distribution of the streamlines, the velocity in our wind tunnel, let's just draw some vectors. We're going to apply some disturbance to the velocity field. Now this disturbance could originate from anywhere. For example, if you had an aerofoil in the middle of your wind tunnel, effectively that is creating some disturbance in your flow field, which is going to affect the streamlines. And we're going to look at how the magnitude of that disturbance affects the shape of the streamlines.